Very good. Questions about homeworks. I have already checked the homework of those of you who have submitted via email their work. Do you want me to send you by email the result, or do you want to discuss something?
Email, I guess.
Email, all right, okay. Yeah, then I will just send you by email what my check showed. But if you have any questions, difficulties, ask now.
Yes, I was slightly confused because you gave us an interval. So were we supposed to find the value of the standard deviation, or were we supposed to derive the formula for the standard deviation? That is where I got confused in the second question.
Yes, you should show me how you derive a formula for the standard deviation of the. I understand, and from what you write, I can see that many of you have just checked Wikipedia page, what is triangular distribution, and it already lists the formula. But what I wanted to see is that you know how to obtain these formulas. Okay.
Okay, then I will send that to you later. I might have to discuss it with you.
Okay, if you need to discuss it, you can schedule with me also a personal appointment that we discuss so that we can discuss. Very good.
Thank you. Thank you.
Other questions about homework? I'm asking because today I'm going to give you a second round of homework. Okay. Yes?
Hello. I have a question about the Manhattan distance probability. So from my answers, I just enumerated all the possible microstates for each macrostate. But there should be is it okay? Or there should be a...
Well, your homework was, I remember your homework was all right. You solved this problem. So it was correct. Can you, what doubt do you have? Do you have a doubt that this was a correct solution?
Yeah, so should there be an equation wherein we use the...
You mean, okay, I see that. No. I mean, what you showed was, I was asking the probability of macro states. I mean, most of you merely calculated by hand all possible configurations and then calculated probabilities. That's enough. Yeah.
Okay. Okay, thank you.
All right, no other questions? Then let's begin, yes. Today, let's talk about first and second laws of thermodynamics. Last time we discussed a little thermodynamics, the zeroth law of thermodynamics. Who can tell me the first law of thermodynamics? While I'm opening my whiteboard. What is it about? The first law of thermodynamics.
The transformation of the energy.
What of energy?
The internal energy.
Infinite energy?
Yeah, internal energy.
Internal energy, okay.
Yeah.
Internal energy. Yes, it is about internal energy. And what does it says? So last time we denoted internal energy, I think, E. And what the first law says about internal energy, Boris?
The internal energy cannot. The internal energy cannot be.
Relax. Formulate your idea about internal energy.
Since when we have the kinetic energy can become the potential energy.
Well,
internal energy cannot.
Just a second. Let's go a bit back to the thermodynamics. You know, in the times when thermodynamics was developed, no one knew about the fact that there are molecules and part of energy can be in the form of kinetic energy of molecules. So people formulated thermodynamic law, the first law of thermodynamics, without referring to kinetic energy or potential energy. How did they do it? Yes?
So it's basically the first law of thermodynamics in very simple terms is about the conservation of energy, that energy can neither be created nor destroyed,
Yeah.
and that if you add any type of energy, let's say heat, to a system, that it's equivalent to, the heat is equivalent to the work done by the system on its environment. So the energy remains constant in that sense.
Okay, so so you are talking about conservation of energy, and in principle, that law, like conservation of energy, conservation of mass, they were predecessors of the first law. The point here is that a consequence of this fact that energy cannot be created, it only can be exchanged. So if internal energy of your system changes, that's dE. So we are taking, we are describing a small change of internal energy of our system. Then it could happen in two ways. Which ways, Kaya?
I'm sorry, could you repeat that?
There are two ways by which internal energy of a system can change. Which are? All right, don't worry.
Thermodynamic processes like, as I said, adding heat to it or extracting heat from it, right?
Okay,
Either
heat.
you add heat or you extract heat from it.
Okay, dQ is heat. Let's
Yes.
denote. And that's all? That's the only way energy can change?
No, also the work done like by the system. So it has to come into equilibrium with its surroundings. So it'll do some work to, become in a steady state again.
Yes.
So yes, minus dW.
Yeah, so exactly, dEW. So the first law says that energy of internal energy of a system can change in two ways. Either by exchanging heat with the environment, or by performing work. Sorry, the other way around. There is always a sign of convention. So if let's define our work this way: thermodynamic work as this, P dV. Pressure, pressure and volume. And then it is minus P dV, okay? And then if system volume is increasing, its internal energy decreasing, and then the work was extracted from the system, right? In this convention. Sometimes people may use a plus sign here and plus sign here. Then it all comes to the definition of pressure. What do we call a pressure? But let's use this notation. Okay, except thermodynamic work that concerns change of volume. Anna, do you know other types of works that can be performed on the system? Anna.
Yes, I'm listening to you.
Yes.
Other type of works, like electrical work?
Yeah, electrical work too, okay. But electrical is very fancy, something must more often occurring in the nature, for instance.
Like general work, like a friction or something?
No, I don't, friction is not what I'm talking about. Okay.
Or probably change of pressures, are you?
No, okay, that's all right, don't worry. We can also change the number of particles. It's a chemical work.
Okay, a chemical reaction.
So we consider energy as NV, right, as a function of N and V for the moment, okay? Yes, and something else, there appears, okay? So these terms, this explain how the work changes when the system exchanges with the environment with number of particles and volume. And originally, yes?
Since you know, if you have a system and if the system works, that means the system will lost energy and we use minus work. Now, you add the chemical energy. It is possible to subtract.
Add kinetic energy, but
I said,
what kinetic energy?
I said
chemical energy.
Chemical.
Yeah, chemical energy.
Well, chemical. So internal energy, so is already counts for chemical energy. Okay. So the particles, for instance, if we speak that we have H2 particles, hydrogen and oxygen, O2 molecules together inside, they already carry an energy. They can recombinate and create H2O. This is the process of burning of hydrogen in oxygen. It's explosive reaction that creates a lot of energy, and then this energy becomes microscopically kinetic energy and pressure. But that energy was already inside, so it is already accounted in this term. So I don't need to add here anything else. This is the first law as it was formulated originally, when people actually did not know about molecules, and some people doubted that they existed. Okay.
And what happens if inside the box you have the destruction of the particle?
Distortion of the particles.
Destruction of the molecule, because you said, okay, we can have hydrogen and oxygen. We can combine to form the water. And because we have the combination, we have energy. We need to add the chemical energy. And what happens if we destroy the water to two particular, H2 and O2? We will still add the energy.
Well, that's it. You cannot just destroy them. There is a law of conservation of energy and the law of conservation of mass. Particles, matter, mass cannot just disappear from the system without trace. So they only can disappear if they go from the system in the environment, or for instance, if we speak about various particles, there were like two kinds of particles that recombinated and become a different kind of particles. But the energy in this process, it only changes forms. Okay, there was like kinetic energy and some energy of which was already inside hydrogen and oxygen. Then they recombinated, and because of this recombination, there was a lot of energy released, freed. So this energy is not needed inside the for creating a link bonds in the water molecule, for the water molecule. And this energy will be transformed into kinetic energy, pressure, in other forms of energy, but it will be inside the system unless you extract it from there. So unless this system will somehow leave the system. And this actually will be either work, okay, one of the things that one of the technologies that is that is being developed is actually hydrogen fuel, right? That's because you can burn hydrogen and extract work, because hydrogen becomes water when it's burned, and the energy that is released can be extracted. And it could be released just as heat, okay? So now, actually, originally, the people were thinking about mostly about work. So if you think, right, about very simple system like a spring, okay, then if you push on this spring, which linear spring with a stiffness K, then you do work, right? So that you can describe a potential energy of the spring as a potential energy of the spring as the extension. Okay, let me call this extension X, and times X squared times the stiffness over 2. Okay, so if we applied displaced, so compressed this spring, the energy of the spring increases. However, if we start to do such experiments, we notice that when later we release the spring, we notice that the energy which we extracted later was less if we make detailed measurements. And at first, actually, there was, maybe you have heard long ago, there were theories trying to interpret this loss and gain of energy as a chemical, as if system exchanged with the environment calorie, okay, like heat, but this heat was in their idea a chemical, like an element, but such element did not find its place in the table of elements because it does not exist. Then it was Clausius who suggested to explain the heat as a change of a quantity that he called entropy divided by temperature. Okay, this is a little funny that at the time, basically, all what the theory could not explain, we tried to place in this yet bizarre object, a bizarre quantity that Clausius called entropy. And then later, it was basically the first problem to solve is to interpret what is this quantity, how it manifests itself in physical systems. Okay.
I think the question is ds is equal to dq over t.
Yes, sorry, you're right. Yeah, by the way, you're right. Thank you, Anna. Yeah. So it's dq t. Okay. Then, yeah, temperature we can measure, and then this quantity that we still that we will discuss today. First about, yeah, I want again to iterate with this example with the spring. Let me put it a little away. So pressure, what is the definition of pressure? Who is around now among the participants and did not talk today? Ivana, I don't know if your connection allows, but if you can.
Yes, I'm here.
If you can, what is pressure in mechanical terms?
Pressure is the force divided by the area.
Force divided by the area, okay, right? So basically, if we consider a cube and we apply here force on this area of size A, then pressure is forced by the area. Then if we actually would have considered two-dimensional problems, pretend that we are beings that live in two-dimensional world, not three-dimensional, what would be equivalent of pressure? So this would be a 3D pressure. What would be a pressure in 2D? Ivana, could you try to answer that?
You can equals the area to the dimension, like the d of the.
So that
the
would
length.
be force. Let me help you. And then.
Okay, divided by d, that is the distance between, or the length of the square.
Length. Yeah, the length of the square size. Okay.
And
yeah, very good.
Yeah.
You don't need to multiply actually. That's just it. If we just need to understand how this force acting on this area distributed over a length of L. Here it was distributed over a surface. That's why we divided it per surface. Here we can in 2D we can define it with the length. And finally, okay, Ivana, what happens, do you think, in 1D?
Well,
we are in
I
one
don't remember.
dimensional world.
Only the force between divided by a point. I don't know.
Point? Yeah, nothing. You just don't need the point. It's just a force. So yes, that's it. So in principle, we can consider, and it's quite legitimate, we can consider a problem in thermodynamical terms, a problem where we have just a spring, okay? It's just a toy problem. Is a toy problem. with the spring. Okay, and instead of pressure, I will use just force, mechanical force. Okay, we can compress the spring by applying force, or by releasing force, we leave spring to find its preferred extension x. Okay, so in this case, actually, work would be this. A term, if you know, in mechanics, work is defined as force times the displacement. In one dimension, the displacement is always along the direction of the force. And then energy of the spring could change in as this. Okay, so this is our mechanical work in 1D. Okay. So now, suppose I took the spring. Okay, first the spring finds its equilibrium position. Let me call it x naught. Okay, and then very slowly we compress it to this value of x. Then energy, okay, delta E would be kx squared over 2 plus, the new energy. So let's go like that. What is the new energy? The new energy is k x squared over 2, which is k, let me call it delta x, k delta x, x naught minus delta x squared over 2. Okay, so it appears like we compress the spring. Okay, but now let's go a little ahead before we started to speak about particles. Suppose that this spring microscopically consists of particles. So basically there is a particle and another particle, and there are many particles that constitute this spring, and these particles are connected by little springs between them. Okay, then each this spring, let me use capital K, has stiffness K, and therefore the distance between particle, let me call it R, is also so the energy of each such element would be K R squared over 2. Okay, so if we take these elements of the spring and make them, place them so there was a large distance R, but we just somehow managed to arrange them in a smaller distance R. So this R naught, and R is a smaller distance, and applied just enough force over here so that they are in mechanical equilibrium and have zero kinetic energy. Okay, nothing changes, right? They are in equilibrium, zero energy, and force acting, for instance, on this particle from the right spring and left spring are equal. Now, however, if we begin this experiment when the particles were extended to full length, okay, to x naught, if I just quickly compress the spring, will they go into such configuration? Idris?
Yes.
So they will, you think so? Now, let me give you a prompt. There is kinetic energy. So if I just compress one, so there are many particles connected by the spring, and initially they have zero kinetic energy, okay? And then suddenly onto the rightmost particle, I suddenly applied at time 0, at time less than 0, force was 0, and then at f t greater or equal to the 0, force some value a. Just quickly compress the spring. What will happen to this spring? Here we have.
Particles will move.
Yeah, they start to vibrate. So first, yeah, so if we watch it in time, after some small time, this particle has not yet received any signal.
Yeah.
It did not move. This particle moved and creates a force on the second from the right, towards the wall. Yeah, and in time 2 dt, this particle starts to move. It acquired some velocity. Okay. So the point is that when we try to deal with a system consisting of many particles, many degrees of freedom, when we try to apply work, there is some work which goes into compression. So we just increase the potential energy of the spring. But there is inevitably a loss of energy because we start to excite vibrations. So these particles, they start to vibrate. We maybe don't want to do this, but it's an inevitable consequence of the fact that there are many degrees of freedom. And in fact, so for instance, we have just two particles, okay, connected. And we now say that the volume of the system, which is length of the spring, is fixed. How many do you think configurations that realize, okay, R1, R2, this is extensions of this slit in the spring. How many configurations you can find that realize this particular case when R1 equal R2? Kyrell, how many configurations in system of two particles you could find?
For the vibration,
sorry, I'm asking Kyrell now.
Okay.
Okay, so only two?
Two? Which? Okay, first configuration.
There are two particles.
Ah, two particles, but they're indistinguishable, okay?
Okay.
And actually you cannot swap them.
Okay, okay, so only one.
Only one. But how many you can find that a particle has, let's say, they have this extension? Yeah, sorry, I forgot to mention also that they have zero momentum. What I'm trying to say is that there is only one configuration when these particles have no momenta. So this particle doesn't move, has zero velocity, zero momentum. This particle does not move, zero velocity and zero momentum. But there are many configurations which will have the same value of energy. So the Hamiltonian would be the same, p squared over 2m, and the kx position kr1 and kr2 squared over 2. There are many configurations in which you can realize the same value of E. But this particular configuration will be very unlikely. So if you consider a whole ensemble, we discussed microcanonical ensemble of two particles. Okay, when R1 equals R2 and P1 equals P2 equals 0, there will be only one configuration, and there will be lots of configurations when particle is here, another particle is here, and the energy which is lost due to extension, R1 is not equal R2, and P1 is not equal P2, not equal 0. Such, most of, of all the possible configurations, you will observe most of the time these configurations. And you will never observe, practically never observe, if you, a configuration in which they just equally at equal distances. Okay.
So
yes,
the configuration is about the energy of the system, or
yeah. So if I fix the energy in microcanonical ensemble is fixed, Yes, energy is fixed, but the configuration in which energy is E and the particles have this exact extension and zero momenta is only one. And there are many possibilities in this microcanonical ensemble to create a system in which the particle is displaced and they have some momenta. Okay?
With the same energy.
With the same energy.
Okay.
Okay?
Okay, sir.
Yes. So now, actually, the point here is that the loss of energy, what we will try to show is that the loss of energy to this excitation of internal degrees of freedom actually leads to the concept of entropy. Yes. Do you have other questions? No questions? Okay. Next. Second law of thermodynamics actually says that this quantity S, okay, in a thermodynamic process always decreases, or does not change or decreases. Again, as we will try to understand, the fact is the same as in this experiment that with the spring that I try to compress. There will be energy that will be lost in the form of excitation of other degrees of freedom. So it's not everything going into a compressed state of the spring, that if we release the spring, it will give us back this energy. Yes. Okay, let's recall again what we were telling about the microcanonical ensemble. So if we have a collection of particles like ideal gas, and all of them, we defined N, V, E, right? So N number of particles is actually constraint. You see, if you recall our problem of eggs in the cartoon, if we have a carton with many cells, right? Imagine that there are lots of cells. The more particles we add, the more microscopic configurations there will appear. Okay, so N provides an important constraint that this is the information that we can use to decrease uncertainty of possible states in the system. Same regards the volume. Okay, if we have let's say here 8 equal cells, or we make our systems twice as large, and we will have instead 16 cells of the same size as in the smaller system. We have increased possibilities for particles to occupy, to take various microstates. Who tells me, okay, for instance, Said, why did we introduce energy? What does energy constrain for us in the system of ideal gas?
I think there is an amount of energy, and the change of energy is important for us when we add energy to system or extract some energy from the system.
Well, that's okay, but what quantities so there are microscopic states of the systems. In ideal gas, if I did not introduce energy, there was some quantity that was more free to occupy whatever values. Who knows what is this quantity? Okay, the phase space of gas, what quantities constitute? So here I described coordinates. What other degrees of freedom did we see in the ideal gas? Said? Phase space of ideal gas consisted of how many degrees of freedom?
In terms of temperature, volume,
No,
number of
phase space has no temperature, no phase space.
Position and momentum.
Okay. Position and momentum, no temperature. Phase space is just 6n. N was the number of particles, 3 dimensions, and there were 2 things, coordinates and moment. So Kaya, I think you pretty much already know the answer. What do we constrain by introducing energy?
Momentum.
Momentum, yeah. Because if there were no constraint on energy, right, we said that, okay, particle could be here or there, and there are 5 particles, but momentum could be just anything, okay? And actually, introducing energy, we, in microcanonical ensemble, put the final constraint that allows already to do some more interesting predictions about momenta, except that otherwise, equal a priori probabilities would tell us that any momenta are possible, right? But if we introduce energy, that's not true anymore. Energy is fixed, and therefore, if one particle takes a particular momentum, it will also have a particular contribution to the kinetic energy. The other particles already constrained to have energy consistent with the macroscopic constraint.
Excuse me, the energy is about the system, but the P here is for the center of mass of all the system, or?
No, it's not. Phase space consists of 6n. Each particle, each of the n particles has 3 momenta and 3 coordinates. Okay.
So the energy must be for each particle here.
So E is Hamiltonian of xi and pi. Okay. And the energy is sum over I pi squared over 2m. Suppose walls are just produce no energy, okay? Each particle will contribute pi squared over 2m. And if I know that particles p naught has value, let's say 2, okay, whatever arbitrary units, okay, then I know that the rest of the particles must sum up to a value which is less than p naught squared, okay? If there was no constraint that all the system must have this value of E, I could put any values of pi, whatever you like, and the energy could be anything, right?
But Steve, for now, we can have different momentum for each particle. How we can put it
so suppose I have energy equal to, okay, mass arbitrary units, let's say, then mass of 2, we have 2 particles, okay, and we have mass 1 arbitrary unit, and I tell you that, okay, that energy is fixed in this case, okay. Now tell me, can I have particle 1, okay, has momentum 4 and particle 2 equals momentum 2? Can I have such configuration? Can you find such configuration that energy would be 2?
No. Yeah,
no. Okay. So if there was no constraint that energy must be 2, I could put 4 and 2, and that's all right. But if I know that energy must equal to arbitrary units, then the only the cases, for instance, would be P1. This is not valid, but this P1 and P2 equals 1. Okay. Sorry. No, 2, because I need 4. But no. Okay. For instance, if I put here 1, then the other particle may have only momentum, which is which is 2 minus 1 over 2. So it's only can have value 3 over 2, right? That's all. So we introduced constraint that already limits limits the number of possible configurations in the system. Those particular parts of the phase space which are described by different momenta. Other questions? All right, so what was done in the theory of statistical mechanics to explain the tendency of systems to go into equilibrium? So we were discussing the spring in which there was only one configuration that was particularly interesting, but many other configurations with strange values of extensions and momenta. And what was proposed to say that if we leave a system, let's say in very, for instance, if we leave a system in a very strange configuration with all particles in one part of the system, this would be a very rare configuration, okay? Very strange. And then in the whole ensemble, in the whole lots of members of this ensemble, all possible configurations with the same value of energy E and VE, we would observe anything like that, very highly disordered state with particles everywhere. So to say, as we can say, a typical value. So typically, if you take a box of gas, it will have many various configurations, but all these configurations distribute, most of these configurations typically distribute particles equally likely somewhere uniformly in the box. Configurations of a system in which all particles for some reason assemble in part of the box are rare. And that's why we don't observe it most of the time, unless we take special care, we spend work to compress the gas, for instance. And the idea, physical idea in intuition was that equilibrium is the state, is the most typical state, the state, such macroscopic state that has most likely value, okay? And when we when we calculated, for instance, Manhattan distance, we saw that, for instance, most typical value was m equals, I don't remember, 1, I think, right? Okay, m equals 2. 1 and 2 were the most typical value. And very unlikely in that system you could find m equals 3, okay? And so this macroscopic state in the cartoon problem, we would consider not typical. And just randomly taken, cartoon would be in a state of m equal 1 and or m equal 2. Similarly, equilibrium, when the system goes to equilibrium, when we leave a glass of water, it will with time go to one of the microstates which has particular macrostate which has particular property. Is its measurement of a macroscopic variable like temperature or other macroscopic variables that we want to measure, angular momentum, would be that of the most likely state. Okay, second idea that was proposed by Boltzmann is to define statistically entropy. So it was basically his insight that entropy of the system, he said, is simply the number, let me call it, omega, I won't be able to write very well, but better I will use W, okay? W, and we already used it in the cartoon problem, is logarithm. So he introduced, there is some constant, which today we call a constant of Boltzmann, Boltzmann's constant, a number of microstates with the given NVE, okay? That he suggested this quantity he proposed as the definition of entropy in thermodynamics. And now we have actually all ingredients to try to see how under this, with this all ingredients to see how the thermodynamic behavior emerges in the microscopic ensemble. We assume that equilibrium is the state of maximum probability, is the most likely state, and entropy is defined using this quantity. Just a little exercise. How? In the first lecture, in the end of the first lecture, I was a little sloppy. Actually, when I defined the microcanonical ensemble, I said that to count states of a microcanonical ensemble with continuous variable, we would use delta function. This is true. So H, Q, and P, i's, minus E divided by n factorial for the number of particles, okay? Now, that's a way, this is almost probability. Unfortunately, this is not the probability of configuration yet, because Anna, what do we need to do with the probability to ensure that it's a real probability density? Anna?
Look at my, what did you say?
What do we need to make this
to normalize?
expression? Yeah, we have to normalize, okay?
Something that I didn't do in the homework.
Yeah, exactly. Okay, W, V, and E. So this is the way we can count the number dq's. So it's integral over all possible qi's and pi's values in the V and consistence, in the V and all possible momenta, actually momenta.
Excuse me, yes? I am somehow lost. Could you review from the Boltzmann formula till now very fast?
So the Boltzmann formula, yes, here, this formula that was proposed as definition, okay? There is no derivation of this formula. So we just go in to check that this formula is a good definition of entropy, all right? And how we're going to check? We see that in microscopic ensemble, microcanonical ensemble, we will find all the structure of thermodynamics. First, zeroth, first and second laws. Well, second laws is actually the most difficult law to explain theoretically. So for second law, we only assume that entropy increases in the processes because it will go into the system will go to a state where W will be the maximum, okay? So we are now just calculating for a system like ideal gas, how to calculate the total number of microstates using delta function, okay? Minus E. And we need to integrate this number and divide it by n factorial. So this integral actually would give us a number of states in the microcanonical ensemble, okay? Questions about that? Okay. No questions? Yeah. Another name, by the way, we will use it. This is also called microcanonical partition function. Partition, that's because it's just partition functions is usually normally the constant which normalizes a probability distribution. Because we normalize microcanonical distribution function, that will be microcanonical partition function. And now let's see finally how the zeroth law emerges in the case of microcanonical ensemble. We take a large, I think, so in zeroth law, what tells us the zeroth law is that if we take two systems, place them in the put them into contact with each other, and allow only into thermal contact, so the systems can only exchange energy, then they will come to equilibrium state, at which there is a macroscopic variable temperature, which will be equal in the two systems. How do we interpret this problem with the help of microcanonical ensemble? So we say that we have actually two systems separated by a wall. A wall such that these systems somehow can exchange energy, okay? But not particles, and the volume, this wall cannot move to make one compartment less than the other. So we can also say that this is a subsystem 1, and this is subsystem 2. And we think that these two, why I say subsystem, because we think that the whole system, which consists of these two compartments, these two subsystems, is a member of microcanonical ensemble. Okay. Then because this system is the whole system is in the microcanonical ensemble, we could calculate the partition function, the number of states for the whole system, or we could say that the total number, we could express the total number as a product of, partition functions, or the counts of microstates in the first subsystem, given its energy equals E1, and so is the product of two numbers of states, W1 and W2, which are functions of number of particles in the first and the second systems respectively. And because we are in the microcanonical ensemble, the total system is the sum of the two energies. So, yes?
You can see what you are writing now.
Oh, because it's too low?
Yeah, it's down, too down.
Too down, I see.
Also, is it a sum or is it a product?
Okay.
The partition function should be a sum, no? Not a product.
No, the partition function will be a product.
You've written a plus sign.
A plus for the
no,
energy.
that's a T. That's
yes.
Okay.
So we have constraint, okay? The microcanonical constraint for the total system is that energy of the first subsystem plus energy of the second subsystem give us the total internal energy of the total system, okay? But the number of states so this number of states that we have calculated will be a product, W1, okay, let me write, times W2. And W1 depends on N1, V1, E1, which describe the first system, first subsystem. And respectively, there will be number of states that the second subsystem can occupy at given energy 2. Is it clear? Please, Boris, do you understand so far?
Yes, but I don't understand really the product. Why it's the product?
Why it's a product? Okay, so that's a good question. So let's try to understand why it's a product. Let's come to this thing, okay? So we have, let me use a different color. So 2 carton with 4 states, okay? And now the point is that there is only 2 particles, but I said that red particle, there is a wall, and red particle can never occupy any state in the black part, in black cartoon, okay? So, and there is particle, there is a black particle that is in the black carton, okay? And then, how many states this particle can occupy, the black particle can occupy? 4, right. So there are 4 states that black subsystem can, 4 microscopic states of the black subsystem. How many the red subsystem has? Also 4, right?
No.
So what is the total number of configuration that the whole system consisting of black and red will have?
4 by 4.
4 by 4. So you take, we place particle here. You place particle in this quadrant, and then you count 1, 2, 3, 4. Then you place particle here, and again you will have 4. And then you will count, sum this up exactly so many times as there are various configurations in the black subsystem. And there were W1 was 4, W2 was 4, and then the total W was just V1 times V2, right?
Okay, so
Is it clear?
yeah.
So it's a product, okay? It's a product. And okay, and then our first assumption about the equilibrium is that our total subsystem will with time relax to equilibrium, and we interpret it as it goes to the state with the most likely probability, all right? How can we find the state of the most likely probability? So first of all, in terms of the W's and the partition functions. In terms of partition function, okay, what is it? The state of the maximum probability. Okay, so we calculated now actually W of N1. The total of the total N, V, and E, given that E1 and E2. So this product, okay, it is not the whole partition function. It is still only partition function. Okay, since we don't exchange any matter or to work, I will just use energies inside. So everything will be just a function of energy. Is the only thing that can change here, right? So we have calculated number of states by this product, given that the first system had energy E1 and second system had energy E2. Let's also simplify it a little. So we know that E1 plus E2 equals E, and E is fixed, right? Therefore, we can rewrite this as V1 of E1 and V2 of E minus E1, okay? So now finally, this is number of states when we fixed energy in the first subsystem and in the second. Ivana, can you tell me how to, Ivana is around, I hope, yes, I see her. So how to calculate of a number of states when E1 and E2 can take any value under this constraint?
The numbers of states, I don't remember.
Well, first let's consider, so what values of energy E1 can take, okay, Ivana? What values? Can it be -1?
That I don't understand.
Well, and when we speak of energy, we usually assume that energy cannot be absolutely like infinity, minus infinity. It can go down to negative values, so there will be some minimum of energy. Let's assume that it's 0, so energy E1 can be 0. And what is the maximum value that energy E1 can take?
The maximum energy, that it's E.
E, exactly. All right. Then here, so this E1 here can be anything from 0 to E. And E2 we expressed as a function. So how to calculate the number of states if we know this number or this expression? Just how do we calculate the total number?
We fix energy E1.
Yeah,
and then we choose all the energy E2 that satisfies the condition that E is
here it is. Yeah, we did this over here. Okay.
Yeah.
Next, what we do, so this is this product expresses just okay. I say E1, for instance, equals 5, and E equals 10. E1 equals 5, then this is equals 5. Okay, so I know how many states in system 2 there are when E2 equals 5, and I know how many microstates there are when value of E1 equals 5. But if I change the value of E1 to 4, that will be a different number, and this will be a different number.
Yeah.
But I want to know that irrespective, when E1 and E2 can be just anything between 0 and so that
we make sum over the condition that E equals to 10.
But because energy is a continuous quantity, what do?
We integrate.
We integrate. All right. dE of V1 E1 times V2 E minus E1. Not that, I gave you a formal expression with the delta function, but it doesn't mean that I need to evaluate it. It's just whatever this number is, I know how, if someone gives me W2 as a function of E minus E1, I can perform this integration. Okay? So now, that's the total number. And what is the probability that my total system in such state that E1 equals, for instance, 4 and E2 equals 6 then? What is the probability? So if I know the total number of states in the whole system, in the total system, and I know number of states for configuration like E1 and E2 equal E minus E1, how to find this? Dionessa, do you have idea?
So,
sorry, Dionessa, I forgot about the breaks. No one warns me. Let's make a 5 minutes break, and you can also, while stretching, have a thought. So, how to calculate the probability of a particular configuration of E1 equals 4, E2 equals 6, if we know W of E1, E2, and we have just found what is the total W of E. Okay, so this is this quantity, and this is this quantity, and I need to find this. Have a break. So after the break, I'm repeating, we in the break many questions we have received from Denessa and from Anna. Let's review. What is partition function? Is anything that normalizes a probability density. Usually in statistics, it's understood as a constant. Like this is, I would say in statistics, this function is a kernel. Kernel, you don't really have to remember it, but often this is called kernel. Why kernel? Because in general, this expresses the right, the correct shape, right? It will be already the correct shape of a Gaussian, this function, but what is missing is the normalization. So we need also to ensure that the area under this curve is 1. And we do it by integrating this function okay, and we get the constant C. So in statistics, often we may call this mathematical physics. This is often called partition function. Okay, so partition function, which I introduced, is a very specific partition function. Is partition function in the microcanonical ensemble. So far, we have been talking about only one partition function. There will be several ensembles that we discuss in the course, and each ensemble will have its own partition function. Each of them has a physical meaning, interpretation, and useful properties, but they are different partition functions. Okay, and first, and actually this is already quite a physical property. The microcanonical partition function is a total number of microstates in the system, right? So W of NVE, the total, is the partition function, but it's also a number of states for the microcanonical ensemble. Okay. Now let's again iterate a little with the problem of carton. Okay, eggs in the carton particles. Okay, you remember that there were a total number of 15 configurations. That's, if we speak of carton as a microcanonical ensemble, it's a partition function. Okay, this is a number of states given the constants. Okay, we'll return, by the way, to this problem today later. We have not so much time, but okay. Now, when I introduced Manhattan distance, that was a macroscopic variable. Okay, so there were many states that gave you the same value of Manhattan distance. In our system that we have defined of contact of two subsystems, we have a macroscopic variable, which is the energy of the first subsystem. Okay. Now, we don't know exactly what is the system. There will be many microstates, but we can measure this value, and it will be different for various microstates. Okay, so we defined that total energy was 10, but E1, like Manhattan distance, could be anything between 1 and 3 in this carton problem. In this problem, it can be anything from, in this problem of thermal contact, is anything from 1 to 10. And E1 is actually labeling macrostates of this total system. Okay, and now I'm asking you how to calculate the probability of a particular macrostate. So we have in the previous page, oh, there was an empty page. So many. So we here have calculated the partition function, like the number of like 15 in our carton problem. We have calculated here. We have calculated the number of macros. So it's the number of microstates that give you a given macrostate of a given energy E1. Now I'm asking you, what is the probability of observing this macrostate? Does anyone want to answer this question? Boris? I'm sorry, you have it all the time in the screen. I don't see all the participants. Let me ask you.
I'm thinking about the probability condition, but I'm not sure.
Okay, let me put, so, okay, let me put here, it is the number actually of
all the
just the number, like we found, okay, Manhattan distance equal to was, I don't remember, 6, or 7.
6.
So how we found the probability of finding macrostates with Manhattan distance 6, with the Manhattan distance 2? We just did what? The number of microstates of this value of energy, okay?
Divided by the total.
The total. Yes, divided by the total. Okay. The total is actually a constant. It's just a hint. And now I'm asking you, so we have agreed, okay, we want to interpret the equilibrium state as the state of the maximum probability. What is the most likely state which we want to interpret as equilibrium? Which has which property? Okay, it has most likely, what means?
Bigger probability. It means the
Yeah.
E1, E2 is bigger.
Yes, so we want to find such state that has maximum of the E1, the maximum number of states given E1, right? Who knows, in mathematics, you, I think, have to pass soon, to refresh soon, how we maximize a function.
We use
We
the
find
Do you want to find the derivative of the function?
Yes, yes. So I want.
But I still, okay, so I'm lost.
Yeah, okay.
What are we doing
where?
again? Why are we doing this?
So I'm trying to show you that the thermodynamics can be interpreted, the laws, empirical laws of thermodynamics can be explained by a model of macro-canonical ensemble. First, I want to find, so first I said that equilibrium state will be the state of maximum probability. And now I want to find what is this state, okay? Just how to find it mathematically. In mathematical terms, I want to find it, okay?
Mm-hmm.
So now we have discussed to find it, I need to maximize the number of microstates, okay? The equilibrium state will be that one in which we have W of E1 and E minus E1 maximum. We apply differentiation rule, but wait.
But weren't we finding probabilities?
I guess, and why did we come to conclusion that we need to maximize W?
I have no idea. Honestly, I'm lost.
Boris has told us that to find maximum, so probability was, so just any probability, disregard this, it's just E1 and E2 equals the number of states with particular value of E1 and E2 divided by the total number of states of the system, right? If we want to maximize it, it's the same as to maximize just this value because this is constant. E is given, number of states is fixed, okay? We don't need to do, we can just disregard the total number of states because it's a constant. So whenever this function achieves its maximum, also the probability will. That's why we want to maximize the partition function, all right?
Okay.
A very useful trick in statistics in general is instead of, so we had this already formula, we found that it's a product of two numbers. There is one very nice trick and mathematical trick is that in statistics is very often used to fit distributions because these numbers in a large system will be huge, like more than Avogadro number. So it's 10 to the many powers. And then if we feed it into computer will just tell us that it does not know how to represent such a big number. So what we do, we take the logarithm of V1 E minus E1, which is the sum of logarithm W1 of E1 plus logarithm V2 of E minus E1, right? Okay, now if we actually multiply it by KB, we will find that this is the Boltzmann this is the Boltzmann definition of entropy, right? So what we are doing essentially by maximizing probability, we also maximize the entropy, okay? So this is already consistent with the fact that systems, when they evolve to equilibrium, they evolve to a state of maximum entropy. So entropy will, wherever you start, you will start with lower entropy, and then you will go to equilibrium, which is a state of maximum entropy, and then entropy cannot change anymore because there is no state with a larger value. Okay, but how do we find it? What is the condition that we have reached value of energy E1? Let me call it E bar, some value E bar, that it is energy of the first system at equilibrium, when the whole system already came to equilibrium. We use the rule of differentiation, right? So then we take the derivative, the total derivative of S B.
Okay. Why have we come back to S?
We came back to S because we want.
How have we come back to S? Like from probabilities?
Okay, again. So we want to maximize P. Is it right?
Yes.
Do you agree that to maximize P, we don't care about W of E? We care only about W of E1, comma E2.
Mm-hmm.
So if we maximize W of E1, comma E2, we also maximize P.
We also maximize?
P, the probability.
Okay.
So when this is at maximum value, like this is also at maximum.
Okay. Okay.
Then we want then, so you agree that we are now maximizing W.
Okay.
No one asks us, but is a common rule that if this number was, okay, this doesn't matter, but the thing is, if we maximize this, it's the same as, if we maximize W, it's the same as to maximize logarithm of W.
No, that, okay. Continue, please. I
Okay,
don't know.
so what I said that to maximize probability is the same as to maximize entropy. Yes, of course we can.
Yes, of course, because that's Boltzmann's constant. So
yeah. If I multiply by constant,
yeah, it doesn't matter.
Still, yeah, it doesn't matter. So I take the derivative of the entropy, which is function of E1 and E minus E1. What do I get? Kyrell, what do I get? What do I write here? How do I proceed?
Hello.
Yeah, so
Get the derivative with respect to
partial derivative. So I fix.
Yeah.
So I take the derivative with respect to E1.
E1. So that is 1 over.
No, I don't know actually what it is.
Okay.
Yeah. Okay. Well, of course, we could substitute instead of SB, we could substitute logarithm of W, but that won't matter. That's not the point of this exercise. Then what do I need to do here? I need to differentiate it with respect to E2 because this is actually E2. And multiply by what? We need to apply. So E2 is equal E minus
negative
D1. DE1. Yes. So we have SB partial derivative E1 minus partial derivative of Boltzmann entropy with respect to the second system energy times DE2. And what must, so in order that when we're at maximum, what must happen? So I need to find such
0.
It must vanish, right? Or that is essentially, sorry, by the way, this is E1, right? So its equivalent is the same as to say that DE1 equals DSB over DE2, right? Does everyone agree? Okay. Now let me ask Said. Do you know what is this? if this is entropy and we differentiate it with respect to E, what do we get? A help. Recall the first law. Do you have the first law in front of you?
Yeah, the first law was the conservation of energy. When we change internal energy, we get work or exchange a heat. But
okay, that's not enough. Then let's put it this way.
And changing the number of particles.
Okay.
Maybe.
Okay. So this is work. We consider chemical work, and so that's basically this chemical. Forget this. We don't have work right now in this microcanonical case. Only energy is exchanged. But what is dq?
Change of internal energy.
No. Yes, but how? Yes. Who wants to answer? Sorry. Anna.
T ds.
Yes. Equals dE plus dV, and then ds over dE. What is it?
It's d over t. dE over t plus dW over t.
Sorry, I should have put partial derivative. So work is, there is no work, right?
And dE over t.
ds, partial derivative of s with respect to partial e. This is the relation. Do you see?
Yeah.
1 over t.
1 over t.
Yes. Oh my God.
1 over t. So what this expression tells you?
It means that temperature of the two subsystems is equal.
Yes, that there is a temperature of the first subsystem and there is a temperature of a second subsystem, 1 over t, but if you want you can take the... And so what did we confirm in this case, Idris? That which law of thermodynamics holds at equilibrium? We had two, actually three, sorry, starting from 0. 0, 1, 2.
Yeah, 0 if
0, yeah. So we said that, okay, when we reached equilibrium, which in our interpretation is the state of the maximum probability, we found the condition that we are at equilibrium. And the condition was that entropy, derivative of entropy with respect to energy in one system would be equal to the derivative of entropy in the other system. As prescribed by Boltzmann's rule, Boltzmann's definition of entropy. And now we also substituted the usual thermodynamic definition of temperature and found that temperature of the first subsystem equals to the temperature of the second subsystem, as should be observed by the zeroth law of thermodynamics. Questions? Hi, may I ask you that you were asking why all this mathematical exercise was performed. Are you convinced that this model explains in a way how the zeroth law emerges in the context of microscopic, microcanonical?
I guess, but again, why did we have to derive all of this?
Well, actually, to convince you that microcanonical ensemble gives you the zeroth law if you use Boltzmann entropy.
Will we be deriving the rest of the laws as well?
Do you prefer not?
It would be easier if you just had the equations on a slide and you shared that with us.
Yes,
because
but unfortunately that I don't have time to do that. That's that would for a whole the lecture it would take time. I had only 1 week from scratch. I never gave this course. Last year actually was given course of mathematics, but yeah, I had to just 1 week to prepare everything.
Okay,
I'm sorry if I sit down. Probably in 2 days I will prepare only 1 lecture.
No, thank you.
Yes, but if you prefer, yes. So again, I'm sure you have heard of microcanonical ensembles somewhere, and the point of exercise is little discuss these things to consolidate again your ideas about it.
Actually, the thing is that, I mean, you already asked us that all of us have different backgrounds. So the ones who have a background in physics still understand things very well, and we know the jargon. We understand the jargon.
Yeah.
But the ones who don't might be really lost in that.
Yeah, that's the point. Yeah, I'm sorry if you really know it already very well. It's not to demean your background. It's only the case that last year we had students that could not follow some ideas because, for instance, they did not remember canonical ensemble. And let's go, by the way, to the canonical ensemble, right? What is canonical ensemble? How do we derive it from microcanonical ensemble? We actually just one step from it. There are actually many ways to derive ensembles. So we still have microcanonical ensemble. Let me call it super system, the total system, okay? Super system. And we have now, before we had like 2 subsystems, which were pretty much the same, but now we want to have only a little, to select only little. So there will be 2 systems, 2 subsystems. There is one which is very large this time, and we call it reservoir, or also it can be called heat bath, because as in the previous example, we will only exchange heat between this large subsystem and this small subsystem, which I will simply now call system. Okay? All right. And the derivation is pretty simple. Now, so we want to find entropy of the heat reservoir. So this is the entropy of the second system, okay? This is energy, epsilon, small epsilon will be there now as E1, okay? Instead of E1, I will use epsilon. This is the system energy, epsilon. Okay, how I would proceed? Because this is very, very small, tiny system compared to the reservoir, okay? I will use Taylor expansion. So about point. So I want to find, so I assume this is an analytic function that I can use a Taylor expansion about the point when the second the heat reservoir had the whole system. What do I write here? Ivana, do you have a suggestion?
No, I actually have a question.
Yes.
About the last demonstration, because I've been troubled always about the 2 systems, and I mean that about the E1 and E2, and I want to know if there is another way to get the same result without supposing 2 systems or 2 separate. I don't know how, if you understand what I mean, because I saw a demonstration about the same and to maximize the entropy, and they don't use the 2 systems, they only use the total energy. And I always
Well, maybe
have,
in my opinion, this is a little simpler. Yeah, there is a derivation like Maxwell. So by using Maxwell Boltzmann distribution, you could do, if I remember correctly, you could do similar things, but using Lagrange multipliers. So you could start to maximize with Lagrange multipliers. Okay. Yes, it's a little deeper result, but we would probably spend a lot of time on this. I believe that this is a little simpler because with method like Lagrange multipliers, we would need to maximize probability and also incorporate constraints using the method of Lagrange multipliers, which you probably do not even refresh in your math course.
Because I always have problems to see the two systems, and I see that after this, we have to make some assumption, like suppose that we can approximate like a linear function, and I don't know why I don't understand this. And when I saw the other way to do it, and I saw like a little and better, I see that.
Well, it's essentially the same. It's just you see that you would start. It's a bit more complicated because, for instance, I don't give you. So usually the procedures that you pretend that your system has a lot of microstates. Okay.
Okay.
And then you can there are many substates, and you put like little patches of energy here. Then you have to come up with the expression for the number of states in the system. Here I don't need to do it, so I just use W. In a way, it's a little more abstract, but it's faster. Okay. Yeah, you can find online. If it is good for you, is that derivation, and you can reproduce it better than this derivation that I showed you. It's all right. I don't mind. It's just the only thing is that you understand the thing that in terms of microcanonical ensemble, equilibrium is the state of maximum probability. So if I take a glass of water, then and suddenly look at it, and it's actually much likely that I find it at equilibrium that in something else, in some other state out of equilibrium, because they never. So there are like it's like very funny joke that is there probability that a monkey sitting at the computer will just randomly type on the computer and write down a book like Tolstoy's War and the Peace? Yes, it is likely, but you put monkey in your life, Stepan, you will never see that it rewrote it, right? And similar things happens with the similar idea applies to thermodynamics. Why you don't observe that all the gas suddenly compacted into like, I don't know, the water, instead of sitting down there, suddenly occupies left part of the cup only. It's probable, but you will never observe it because it's very unlikely. Okay. And then it's already a mathematical statement that if you maximize if you find the state of the maximum probability, you also find that there is an entropy, which is the logarithm of microstates. When it's maximized, the probability is maximized, and then you find that also the condition implies equal temperatures. That's it. Okay. Other questions? All right, then let's continue and make canonical ensemble next time. What today I wanted also to discuss, I will send you a reading. It's from a book of, sorry? Hello? Do you hear me?
Your voice is breaking up.
Okay. Yeah, there was a connection loss, strangely, but now I think it's back to stable state. I will send you by email a reading material. It's from a book of Mehran Kardar that I have advised as possible reading for this course. actually, I forgot to mention that this book was also released as a notes for the MIT course of Miran Kardar, which is also available, by the way, on YouTube. It's a very, I think it's an advanced course. You may follow it. It's an interesting and non-traditional way to introduce to StatMech. But I want you to read about two-level systems. There is a section I will give you just specifically to read about two-level systems. It's a very simple system, and you will have a homework. So homework for now is reading, but after next time, I will give you some problem related to the two-level systems. Okay. Okay. Canonical ensemble next time, and questions if you have. Maybe let's make 5 minutes break, and then you ask questions. Come on.
About my question earlier, so for
Yes,
a partition function, if there is an added freedom, will the partition function change? Or
yes. So basically, yeah, that's a good question, right? I forgot about. So the super system, I was okay, but super system of two subsystems. Okay, I said it's in the microcanonical ensemble, so that in total, again, omega comes to me, that the total number of states is actually fixed by energy n EV. But then, if you change E of the total systems, yes, this was providing a constraint that limited the number of states. If you make energy more, what will happen with the number of states, do you think? Denessa, your opinion?
if you add energy?
Yes.
Okay. So now is it the energy is now arranged?
It's arranged, but think of an ideal gas. Okay, so we said that if you in ideal gas, momenta were limited by energy, right? So if I say that momenta must be zero, so sorry, if I say that there is ideal gas, right? So we did not specify what was this super system, but suppose it's a system of ideal gas somehow, and that's the Hamiltonian. Okay. And I say that, so this is energy, and I say that energy is zero. What are possibilities for values of pi? Everything zero, right?
Zero.
Then I make it 0.1. Okay, value pi equal 1 is not possible, but very small values are possible. Then I take it to 1.5, 100, 10.5. P1 equals 1 is already a possible value. So increasing energy, I increase the number of states, right? With the number of particles for ideal gas is the same. In the case of Carton, in the case of discrete systems like Carton, it's almost the case. When there are 2 or 3 particles, with 3 particles you will have more states. But if you put 6 particles, there will be only 1. But it's just a limitation of that simple example. Normally, you think that if you put more particles, your number of states increases. If you put more volume, increase the volume, number of states increases, and so on. So yes, it changes, and even more. We will not do this demonstration, but actually d log W of dE is actually also the temperature of these whole systems in microcanonical ensemble. Okay. Oh yes, Ivana, go. Yeah, sorry. But if someone else has questions, I'm still here. By the way, if you need to go, you can go. You can finish watching the video online when it's uploaded. If I have interesting questions, ask. No. All right. Yeah. Thank you for attention, and see you tomorrow. You will receive an email about it.